Education Coalition. If it can't be grown, it must be mined. So first of all, I want you to kind of maybe pause the video even and think about this. Maybe make a list of things that that you use that aren't related to something that's been grown from the ground, but is in fact, it must have been mined from the earth then. And I oftentimes run kind of or suggest a challenge with students that I have in live classes is I challenge you in the next week before I see you next time that if you can figure out one thing or bring me one thing that doesn't fit either of these categories, that it wasn't grown and it wasn't mined. And really everything goes back to some sort of mining process. And I would say arguably even the stuff that's grown today, a fair number of our agricultural products, of things that are grown, really need mining for those things to continue in an agricultural or an industrial agricultural process. So even the stuff that's grown comes back to mining. Okay, so Mineral Education Coalition has that saying, and I really like that. I think that's a good way to think about the world around you, to think about the resources that we consume. So here's another one of these, the USGS Platinum Group elements in South Africa. South Africa has most of these, or a huge percentage of these PGEs. There's a mine in Montana, but not nearly the size of these. An inventory suggested 150,000 metric tons of PGEs between the two South African countries that produce the global supply of these crucial metals. And by demands, they've doubled in the last 20 years because these are environmental metals too. If you had a catalytic converter in your car, then you have a piece of platinum or platinum group elements in your car. And that metal is used to react with the NOxes and SOxes as you're combusting fuels in your internal combustion engine. Those can produce noxious gases or nitrous oxides and sulfur oxides that are harmful to the environment. What I mean by harmful is they give rise to acid rain, which remember was a problem in urban areas a few decades ago because of the NOxes and SOxes. But it was legislation or government essentially stepping in, looking at the science and saying, hey, we need to regulate the amount of NOxes and SOxes that come out the tailpipe. And we are now mandated to have catalytic converters and to have smog checks in some states and things like this, so you're not putting out too much pollution into the environment. Okay, I use pollution that way just to say that it's kind of a soft term. It doesn't mean one thing. It doesn't mean carbon dioxide. It doesn't mean NOxes. It doesn't mean toxic waste. It means all of these varieties of things that are pollutants. And NOxes and SOxes became a pollutant because they lead to acid rain, which can be harmful for lakes and streams and animal habitats, wetlands, as well as eroding the limestone headstones or statues in urban areas. So PGEs, or platinum group elements, have been used a lot in the last 20 years to slow down the acid rain and other releases into the environment. And global estimates, 470 tons per year. We have a good 320 years left just by those two mines of platinum group elements at the rate that we use them. So this might seem like a long time, but again, I live in a country that is under 320 years old. So that may seem then like a long time, but this is a very young country, right? America is a very young country as far as in context of the rest of the world. So 320 years is really not that long, and I think this really puts it into context to help us understand how to extend that 320 years, right, of this resource that it seems extremely valuable for our environment. Okay, now to food. If it can't be grown, it must be mined. Well, what if it is grown? What do you need to grow stuff? I don't know about you. I grew up in an agricultural area and mostly cattle, but then in the area that I live today, the western Treasure Valley, this is a corn and potatoes region and sugar beets, right? This is a very agricultural region. And I never let anybody escape in Earth System science classes not realizing that the amount of mining that is needed to sustain these agricultural products is pretty staggering. It is not just plant the seed and it grows, right? Go talk to any farmer in these areas. It's not that simple. That it needs, the soil needs to have the nutrition for that type of crop. Now, once upon a time, being able to break up virgin field or a virgin floodplain and to plant seed into it was basically enough, but not in the soils that we have around us. They're very alkaline. They're very low nutrition. They're basically just a medium for growth or for roots to develop into. There's not a ton of nutrition available natively in the soil. All of that nutrition has to be taken in. Not to say that there's none, there's just not enough to supply the amount of corn that's coming out of the area. Corn, and this, I'm taking the heaviest of the crops to talk about this, but in soils, the nutrients that are needed here, the fertilizer nutrients, the NPK value, or the nitrogen, phosphorus, potassium, that are needed in certain ratios for every plant to grow. Well, the ratio for corn is very high. So I would argue that to do the industrial food model, we have to have a lot of at least those three substances to grow things like corn. We'll talk about the staple food crops in just a second. So of those three, potassium comes from something called potash. And here's a distribution of potash deposits, known ore resources in billions of metric tons. And you can see they're pretty spread around the globe. And then strikingly, there are areas that are high in PGEs, but very low in resources that are needed to grow crops. So it is suggested that potash is not necessarily limited, that we probably can supply global demand for hundreds of years, but it is the supply disruptions and that not every region has their own, like the United States has potash deposits to access, that could lead to the decreased nutrition or even starvation in the future because of things like this. And now this is a really good example to show that food isn't, food and starvation is not just a can you grow it type of problem. It's can you get the resources to grow that food, which is sometimes a political problem then. So the amount of food that's produced in the world is enough to sustain our population and to feed our population, but it is oftentimes politics about that get in the way of the distribution of food. Or the distribution of fertilizers to grow that food. So if you're in an area that does not have the fertilizers to grow the food, then that's a food that you cannot grow, clearly, unless you import fertilizer or import food. And then another one of those is phosphorus. So NPK, we're going backwards here. K, potassium, P for phosphorus. Phosphorus is a fairly tricky substance. Again, this is something that is needed in corn and many other crops at really high amounts. And there's very vigorous discussion and debate around the idea of peak phosphorus, clarifying the key issue of the vigorous debate about long-term phosphorus security. And this is a paper that you can find with the class materials to dig into this material a little bit. But there's this dropping of material, or not down dropping, but minimizing of how much phosphorus goes up the food chain each time around. A lot of that phosphorus is dropped out of the back end of animals and on the way up the food chain. So the amount of phosphorus that we get, that we need for our DNA, that's how DNA and a lot of the biologic processes that occur within our body occur, is because of phosphorus. It's also a very unique electron donor in our body. So we need phosphorus, and for us to get that, we eat that from plants that get that from other sources. So this is kind of the general, a really general, here's the amount that's in Earth's crust, and then how is that distributed, and then eventually getting to us. And this is supposed to paint the picture, and I think this does pretty well, that shows there's only a certain amount of phosphorus that's actually available, period. We live on a finite Earth, and there's only so many people that you can build with that amount of phosphorus, which is way more than we have today, and way more than we will ever get to. So that's not the limiting factor. The limiting factor then is access to this phosphorus. And of course, we're not making humans with all of the phosphorus. We're making cattle, we're making chickens, we're making corn, and then it is those things that sustain us, of course. And there's of course a transfer of phosphorus there. But what we are also doing is taking phosphorus from the rest of the native ecology, or the ecology that once was there before the corn or the cattle were there, and that phosphorus is exclusively being used for human material. So anyway, my point here is just to point out that phosphorus is limited, as are all resources. It's just well shown here. And that there's a discussion about the peak of that material. And that discussion, again, it widely varies. So here's the estimated lifetime reserves. Here's the assumptions that are being made. And here's the citation for each of those. So some vary to as much as 400 years at current rates. Again, 400 years may seem like way long time away, but when we're talking about growing corn and growing food, and something that is like the #1 food resource for at least the Western world right now, that and wheat, we can't think about going without phosphorus, right? This is even if we're living on Mars, right? Even if we're on Mars, we still have to eat, right? So 300 to 400 years, as short as things like 60 years, by some of these estimates, by the mid portion of this century, we may be facing the decline of phosphorus production. So we really do need to pay attention to this, right? To peak phosphorus, because underlying this is our food system. The concept and analysis of peak phosphorus is based on the following premises, and you can just sort of independently read these at some point and to go through these point by point to see what assumptions are being made about when this peak will be, right? We know that peak is a peak, right? That if you buy a candy bar from the store, and you begin eating that, it's a finite candy bar, there's only one, and then you begin eating that, at some point, you're going to take a bite, and you're going to be biting into a portion of the candy bar that there's less remaining than what you have already eaten. So every bite that you take that's next, you'll be eating into less and less until you finish the candy bar. That's the concept of peak oil, peak phosphorus, whatever it is. So here's remaining phosphate peak reserves. Here's a good projection by derived from USGS survey data, suggesting by a peak somewhere around 2033. Yeah. What about nitrogen? The N in the NPK. Nitrogen, doesn't that come from the atmosphere? Remember, the atmosphere is almost 78% nitrogen. Well, kind of. At a time when we did farming practices where we relied on legumes at their roots, they have nodules that contain bacteria of nitrogen-fixing, they're nitrogen-fixing bacteria. And we used to do a method of crop rotation with legumes before corn, so we could get all the nitrogen out of the atmosphere fixed on those bacteria and the not root nodules, and then to plow all that stuff back in, or at least the vegetative matter, so all that nitrogen was then bioavailable, because the stuff that's in the atmosphere isn't bioavailable. You can't just breathe it out of the atmosphere, and the plants can't either. Now, it doesn't all come from just the atmosphere today. In World War II, there was a process that was figured out, the Haber process, that could take nitrogen from the air, or the mix of the air, and combust that with natural gas, and then produce the product ammonia. So ammonia then, which is very high in nitrogen, essentially taking the nitrogen from the atmosphere and making a particle with it, a solid that we could then use later. And ammonia is the #1 nitrogen fertilizer of cornfields, or at least here in the United States, those things that I'm familiar with. So you've probably seen farm fields, or maybe have seen farm fields with tankers. There's maybe a tractor with a tank behind them, and they're spraying something. They're not always spraying pesticides or herbicides. Sometimes they're spraying fertilizers, and ammonia fertilizer would be one of those. So we have figured out ways, knowing what plants crave and knowing what they need, being people who eat, right, conscious animals that need to eat food, we have gotten better and better and better at making sure that we can grow more and more and more food. And then, of course, the the result of that is more and more and more people, right? Because population follows food production or food availability. And this is a really good example of how we took the limitations of nitrogen and needing to do the whole waste of time crop cycling kind of thing, and just totally bullocks that and do it chemically. And this is kind of entering the age then of what we call chemical industrial farming, where pesticides, herbicides, they're chemically developed. You no longer need to go out there and weed the plants or run the moles away. You can apply applications of chemicals to deal with those. And then chemical fertilizers, right? NPK, that we can now chemically amend the soils to give the soils what they need to grow the plants that we want to grow there, rather than spending a long time trying to biodegrade compost and wait for the field to go fallow for a couple years and increase its nutrition naturally before we do it. We don't have time for that stuff, man. We're humans. We don't got time for no nature to do its business. We're humans, and we just need to do that next year. We need 6 onion crops to come out of the fields every single year so we can make our quota and we can grow and grow and grow and progress more and more and more. Sorry, I don't mean to poke too much fun on that. But that is basically the industrial agriculture process in a nutshell, right? Is that we are pushing more and more and more out of the soil because we amend it from other locations, of course, by mining. So of the staple crops, corn, wheat, rice, potatoes, soybeans, and cassava, only one of those is shown up here, but you can see corn is a very high feeder of these things. Grain is quite a bit lower. And then we use, of course, the corn to feed a lot of the animals that we then use for meat. So this is why many people have argued a vegan diet, or at least a reduced meat diet, is a lot more delicate on the environment, and you can probably line this up now. So not only are the animals themselves potentially harmful to the environment, or they absorb a lot of water, they use a lot of water and they foul up a lot of water, but also they need food. And that food, a large percentage of that food, is grown in these methods that take a lot of space as well. They also take a lot of petroleum to keep all the tractors going, and then not to mention the petroleum to extract the material around the world to then concentrate as fertilizers to give them. So the food industry is very much based in mining as well. So if it can't be grown, it must be mined. Well, even if you're growing it, these days, you probably have to mine stuff to fertilize that as well. Now, I don't mean to say everything, right? There's a lot of great agricultural methods out there, and the rise of the civic farming movement, civic agricultural movement, and methods to increase, organic to organically amend crops as well. We are seeing a major rise in that, but this is just sort of the business as usual process. All right, couple more things here. The oil situation, right? Here's another of these delicate and precarious situations that has unfortunately become politicized over the last decade because, of course, burning the fossil fuels leads to increased carbon dioxide that's emitted, and that increases carbon dioxide, a greenhouse gas in the atmosphere, which has led to global climate change that's been detected well into the 50s. The 1950s was the first international conference on climate change, was in the I want to say 1959 or 55, maybe 54. I'm bad at numbers sometimes, but we've known about the potential for this problem for a long time, and then, of course, we've been measuring that problem for quite a long time as well. And then a couple of decades ago, some politicians took it upon themselves, as politicians, not scientists, to go ahead and refute all of this and say that climate change is a hoax, or the terminology at that time was global warming. Global warming is a hoax. And that is very, very unfortunate to us living through the Anthropocene, that we put up these walls around what humans can and cannot do. And apparently, with the process of oil, that doesn't have any bearing on the climate in general. Okay, I better not go too far into that la-la land. Okay, this is what is some like to consider our daily barrel of oil that's over here. And I scaled this generally to size to represent 340 meters tall, 128 meters wide. And this is using 2013 numbers. That rivals the size of the Empire State Building. Pretty darn close. So if you were to hollow out the Empire State Building and just dump oil in there, you would certainly be able to fit our daily barrel of oil that we burn as a global society every single day, which is about, at this time, was 78 million barrels of oil per day. Per day, every single day, 73 million. Now, that was 2013 numbers. I'm recording this in 2019. Oh my gosh, this slide is 6 years old. Wow. I really need to update some slides sometimes, huh? So, yeah, in 2016, which is even kind of old data by now, the numbers that I last looked at were 93 million barrels per day. So between 2013 and 2016, we had increased from almost 80 to 93. So over 10 million barrels of oil in under 10 years we increase daily. So we keep increasing in our amount of consumption of oil through time as well. Every single year we have done nothing but burn a little bit more and a little bit more and a little bit more. And now that's not centralized on one area, one state, one country, something like this, that we certainly vary, right? Different regions in the United States vary their amounts. Different countries also vary their amounts, and so on and so forth. Okay, so there's our daily barrel of oil, and to discuss peak oil, of course, remember, this is a physical principle of anything. Go back to the Snickers bar, the candy